Hello, everyone. My name is Michaela Huffman, and today we're going to be going over Monte Carlo modeling of the effects of impact events on planetary atmospheres, which is my poster at DPS EPSC 55. Let's take a look. Okie dokie. So, this is the poster. And I did this work with Dr. David Brain and Dr. Kelsey Singer, and a postback, Julia Johnston. Kelsey is over at the Southwest Research Institute in Boulder, and Dave is at LASP/CU Boulder. So the main takeaway before we get started is that Venus and Earth's atmospheres shrink and Mars's grows under bombardment. So that's the main takeaway that we should be focusing on while I tell you the overall story. So there are a lot of different processes that affect planetary atmospheres, but one that hasn't been studied as much is impact cratering. And that's because it's a very complex process. There's a lot of different physical processes that occur that can add or remove atmosphere due to impact cratering. We want to look at the net atmospheric change from many impacts, the combinations of gains and losses. Think about it like a cup of water. If I have a glass of water and I drop an ice cube in it, then I will probably end up with more water in that glass than when I started. But if I really huck like a snowball in there, then I could splash out more than I add and end up with less water than when I started. This also depends on the amount of water that's in the cup initially. If it's already close to overflowing, then any amount can reduce the water in the cup. And also depends on the ice cubes. Like if I throw a rock in there, that's probably not going to add that much water comparatively. The same thing occurs with planetary atmospheres and impactors. So there's a lot of different processes that we need to take into account. There's the impactor itself, there's the target body, there's components of the atmosphere, gravitation, whole lot of variables to look at. So what I did in this work is compared and combined these 5 pre-existing models from the literature. And those are these models over here: FAM, Shuvalov, Genda and Abe, Svetsov 2000, and Svetsov 2007. 2 of them are analytical, that's FAM and Genda and Abe, and 3 of them are based on hydrocode results from SOVA, and that's Shuvalov and the 2 Svetsov models. We look at both big and small impactors, fast and slow, asteroids and comets. So we have size frequency distributions and velocity frequency distributions and proportions of comets versus asteroids at each body we look at. And we're examining this during a potential heavy bombardment period when the impact cratering would be the most significant atmospheric change process, like far outstripping, sputtering, etc. Okay, so how do we even do this? Well, if you take a look at this figure over here, we have a size frequency distribution and velocity frequency distribution. This is velocity, this is frequency. Size. And we have it different for asteroids and comets for the velocity. So we pick, for example, a small, slow comet. That means that we should use the model that works best for small, slow comets. Or if we pick a big, fast asteroid, then we should use the model that works best for big, fast asteroids. Or if there's multiple models, we should use both of them and then average the results together. And that will give us one composite answer. That's how we combine them for our composite model. So let's take a look at these models individually. So first is this FAM model, which is also called the tangent plane model. And the idea is that if you have too small of an impactor, pretty much nothing happens. You just add. And then if you have a big enough impactor, it will blow off the entire tangent plane above the impact point. This is also by, this has been edited a little bit by FAM, but originally it was by Melosh and Vickery. So the red line here is loss. This is the impact radius on the x-axis. That's a log scale. And the blue line is gain. The black line is the total change. And the y-axis is atmospheric pressure change in pascals. This is also a log scale. So we have no loss, and then we have some loss. And initially, this model had it so that the gain line would just continue going up. I changed that a little bit so that if you blow off the entire tangent plane, you do not gain from the volatiles in the impactor. And this radius for critical mass changes depending on the planet parameters and like the atmosphere. So if you are changing the atmosphere, then that radius can change as well. For this entire column, all of them are for Mars currently, but I did this for Venus, Earth, and Mars. Okay, Shuvalov is based off of SOVA results, and you have this wedge basically that gets blown off depending on the size of the impactor. And we have loss and gain. For models where gain was not explicitly stated in the papers, we use the sector model, which is from Melosh and Vickery, 1990. So, you gain, you basically do nothing, and then you lose, depending on the size of the impactor. For Gannon and Abe, this is an analytical one. So you have a Mars-sized impactor impacting an Earth-sized target, and then shock fronts propagate through the target body, resulting in a high velocity jet at the antipode. Then you also have vapor plumes and ejecta at the point of impact. Svetsov is based off of SOVA, gains and losses. And Svetsov 2007 is also based off of SOVA, but it takes into account impact angle. Okay, but some of these models work for big things, and some of them work for small things. Like, for example, you probably don't want to be using the Genda and Abe model for something down here that's like 0.1 kilometers in radius. So I went through and looked at where the different models work best, and they most vary on the size regime versus the velocity regime, or if it's a comet or asteroid. They mostly depend on size. So Svetsovs are better for small impactors. Shuvalov is better for mid-range. Genda and Abe is best for really big stuff. And FAM is supposed to work for everything. This N value is just a parameter that changes where that critical radius is for blowing off the tangent plane. It ranges from 10 to 2400. So we just chose one with sort of log space in the middle. But we tested with N equals 10 and N equals 2400 as well. Then the impactor size range that I use is from 0.1 kilometer radius to 1,000. And again, that depends on a size frequency distribution and a velocity frequency distribution. So we're pulling, we're randomly generating size and velocity, and if it's a comet or asteroid, and then picking the models based off of that plot that I just showed down here, and then combining them into the composite model. If there's overlap, then we average the results. Okay. So I did this for Venus, Earth, and Mars. This is Venus. On the x-axis, we have the cumulative number of impacts. So we hit Venus with 1 million impacts. And we're starting from, if we were to do this tomorrow. So this is the current atmosphere of Venus, and we start from there. Each of the colored lines is a different model. So green is FAM, cyan is Shuvalov, light blue is Genda and Abe, dark blue is Svetsov 2000, and purple is Svetsov 2007. The black line is our composite model. So that's when we're only using certain models for certain sized impactors. These other ones are applying it to all of them. So even though Genda and Abe only is supposed to work for really big stuff, this light blue line is using it for every impactor, versus the composite model picks existing models to use depending on the size of the impacting body. The y-axis here is the atmospheric pressure. The x-axis is linear, the y-axis is logged, and it's in pascals. And you can notice there's a solid line, which is the median of 100 runs, and then the dashed lines are the interquartile range for 100 runs. So as you can see, FAM tends to grow, and everything else tends to shrink overall. You may notice this huge gap here. It's because for Svetsov 2007, it automatically tanks the atmosphere down to 0 almost immediately. We'll talk about that in a minute. And then grows from there. But you can see this composite model, it shrinks down and then tends to hang out at a steady state around 10 to the 5 pascals. Okay, let's take a look at Earth. Note that the y-axis is different here. It tops out at around 10 to the 7, but this one starts at 10 to the 2. The x-axis here is the same, 1 million impactors. And we're starting off from Earth's present day atmosphere. So this is like if a bombardment period were to start tomorrow, what would happen? So as you can see, some models grow and some shrink. For example, Genda and Abe's shrinks, composite shrinks, the Svetsov 2000 shrinks, but all of the other ones seem to grow. So we're seeing discrepancies in these data, where some models, if you apply them to all impactors, shrink the atmosphere and some grow them. But with our composite model, which is this dark black line, dark black, it seems to grow for a little bit and then it shrinks. For Mars, note that we are now topping out at around 10 to the 6 pascals. We see growth for a lot of the models and then shrinkage of the atmosphere for Gundanabe and for Shubalov. Here is our composite model, and you'll note that it's a lot nicer. Those interquartile range like error bars are present. They're just really close to the line. But we see that for Mars, our composite model gives that it grows instead of for Venus and Earth where it shrunk the atmospheres. So a couple of takeaways. We see these big discrepancies between the models. Our composite model is smoother for smaller atmospheres, and it seems to grow Mars's atmosphere, whereas it shrunk Earth's and Venus's. All right, well, let's take a look at those plots all together. This is the composite model results. The yellow line is Venus, blue is Earth, and red is Mars. So you can see that Venus's atmosphere drops from 93 bars to 0.8 bars. Earth's goes from 1 bar to 0.34 bars, and Mars goes from 0.006 bars to about 0.12 bars. So Venus and Earth's drop, Mars's grows. So let's talk about this. It seems that our composite model, using all of the models from the literature, tends to grow small atmospheres and shrink large ones. That's very interesting, but they aren't all leveling off towards a single answer, which is good because that implies that the characteristics of the planets themselves and the size frequency distributions at those various planets does matter. We also note that Venus's curve is the most choppy looking. Earth's is a little bit better, and then Mars's is very smooth. We'll talk about that in a second. Another takeaway is the large discrepancies between models. This implies that we need a model that will unite the size regimes and relevant physics. For example, if you were looking at Venus and you just went off of Gundanabe's model, you would say, oh, well, the atmosphere shrinks. But if you went off of Pham's model, then you'd say, oh, the atmosphere grows. So very different results. This is possibly because they take into account different processes. For example, Gundanabe's model takes into account that antipodal jet versus Pham's is just the tangent plane getting ripped off. Another problem that I ran into is that some of these models are perhaps not intended for large atmospheres and small impactors. So I made several corrections to compensate. For example, the Svetsov 2000 model really likes to remove atmosphere when you get really high atmospheric pressure. So for Venus, it just dropped it to 0 immediately, and then that's a regime where it likes to operate, so it grew from there. There were some parts where certain models would blow off the entire atmosphere of planets for a impactor about the size of this conference center, which is non-physical, especially when you get into larger atmospheres. It really likes to do that. And even just looking at these plots over here, you can see that we're getting orders of magnitude difference between some of these things. This is 10 to the 8. So if you took a 1,000-kilometer impactor for Svetsov 2007, then you would add 10 to the 8 atmospheres to Mars. Pascals to Mars. Versus if you look at, for example, Pham, if you took a 1,000-kilometer impactor, you would lose a handful of pascals. So there's significant differences between these models. So I made some corrections to compensate. Basically, if it was trying to blow off entire atmospheres, or many times of an atmosphere, I would just set that value to 0. So this explains why Mars's composite curve is smooth versus Venus's is choppy, because some of these models really like dealing with small atmospheres. And so they produce a very smooth curve when they're dealing with Mars's atmosphere, which is quite small, versus with Venus, you're dealing with all this scatter, because the models don't like acting in a 93 bar atmosphere. So a couple of feature work things. One is to add more models to the composite. There's a Schlichting et al. 2015 paper that does try and connect some of these models across different size regimes. So I'm going to implement that. In addition, this is acting as if we had a bombardment period tomorrow. Probably not going to happen. So it will be more helpful if I set my quote unquote time step. There isn't really time implemented in this. It's just number of impactors, backwards. So we start from the current atmosphere and work backwards in time, to see what past atmospheres would have been like on these bodies. And then I'm thinking that I'm probably going to need to make my own model in ISAIL, which is a shock physics hydrocode, using tracer particles and using a rock layer and an atmosphere. Then if the tracer particles velocities get above the escape velocity, they're gone, and those get removed. And then seeing how the impactor volatiles stay or are removed as well. Here are my citations. I did this work with C. Boulder LASP and the Southwest Research Institute in Boulder. If you would like to talk about this, or you have any ideas of things that I could change or questions, please feel free to contact me. All my information is on the website that this QR code goes to. And I will be here all week at DPS EPSC 2023. So if you see me around, just come grab me or feel free to email me and we can meet up to chat. Thanks so much for watching this summary of my poster. And I hope to see you around. Thanks so much.